So there are different ways that a material effectively can use. And actually, we can calculate the theoretical yielding for a perfect copper crystal. So if a material were to yield, we can simply think about, if I were to shear a system like this, what would be the energy to basically break the bonds of this entire row? And you'd get a yield stress that's approximately 20 gigapascals. But that's almost 3 orders of magnitude different from our actual yield stress, which is about 40 megapascals for copper. So you get this basically difference of your yield, basically your shear modulus over 10, or your Young's modulus over 10. So what is accounting for this difference? Well, it's dislocations. Dislocations exist, so it's easier for a dislocation to hop in between these spots rather than to break the entire plane of interactions. So it's really, really important when we think about essentially these dislocations and defects that exist in our system. So we're going to talk about dislocation density, which is the number of defects per unit area. And if you have a material that is highly cold worked, meaning something that undergoes like plastic deformation processes, so rolling. So if you have two big rollers and you pass metal through these rollers and they basically reduce the thickness, so you can do cold rolling. There's lots of different, basically if you plastically deform any material, you're cold working the material. So cold meaning that you're not elevating temperature when you're doing this process. You can do this when you bend a wire. You feel that it's, number one, heating up, but also it gets harder and harder and harder to bend that wire. So a highly cold work material will have a dislocation density of approximately 10 to the 14th dislocations per meter squared, whereas a highly annealed system, so where you put this material in a furnace, and then you put it at high temperatures for long times, you can reduce that dislocation density to 10 to the 7th. That's 7 orders of magnitude, so that's quite a lot. So this brings us, this whole topic is, we are going to talk about strengthening mechanisms. So we are going to be working with 4 strengthening mechanisms where we are going to perform a process that increases the strength, specifically the yield strength of our system. So we're going to talk about work hardening, solute strengthening, grain size strengthening, and precipitate or particle strengthening. Now, each of these mechanisms, the whole idea is if we can increase yield strength if we make it more difficult for dislocations to move throughout our system. So if I cold work material, I am going to increase the density of dislocations. So you can see here, if I work harden a system, my yield strength is proportional to parameters, but the key one that's going to change is my yield strength is proportional to my dislocation density to the 1/2 power. So if I have a highly cold work material versus a material that looks like this, which one is going to have the higher yield stress? Well, from this equation, it's going to be number 1. But also we see that when I have dislocations close to each other, to move this dislocation, these are basically all of the same charge, like positive, you can look at them as like basically charged particles. They are going to want to repel. So if I have a lot of dislocations, it's difficult for dislocations to move when there are lots of other dislocations or defects or strains in my system, or basically strains in my lattice. So if I have all these dislocations, it's going to be difficult to move this dislocation throughout my material. So if I have more dislocations, it's more difficult for a single dislocation to move freely throughout the system. So that is essentially the idea behind work hardening. I increase the number of dislocations, but by doing so, it makes it more difficult to move those dislocations via stress throughout my system. I can also solute strengthen my system. So you can imagine, and we can kind of see this here with work hardening, and again, you can kind of see it even more in depth. There's this region of compression and tension, so when you're trying to move this dislocation through these regions, it's difficult to move through. I could also solute strengthen my system, and you'll see on the page previously, the change in my yield strength is going to be proportional to my concentration of solute to the 1/2 power. So the idea here is, again, if I'm a dislocation, if I have a perfect lattice where my atoms are just at their equilibrium distance apart, I could kind of move through this system. But if I have a solute, now I've introduced kind of this distortion to my lattice. there's essentially local stress or and strain distortions in the system. So it's more difficult for this dislocation to move through this big region, and even in when I have a smaller solute as well. So those solutes make it more difficult for my dislocation to move through my system. So you see how my yield, again, the yield strength increases because as my concentration of solute increases, it's more difficult to move through my lattice. I can also increase my yield strength by actually decreasing my grain size. So as I decrease, and if I have a huge grain like this, like you can imagine, if I have a large grain size and I still have, let's say, the same dislocation density per grain, like 3, versus if I have a system like this, that's like very small, 1, 2, 3, as I decrease my grain size, it's inversely proportional. So as I decrease my grain size, you see the dislocations are piling up and they're getting kind of squished together. Again, it's much more difficult for those dislocations to move through my system. So my yield strength increases, as opposed to, again, when I have a large dislocation, a large grain size, where, again, you're not going to see as much dislocation pile up because they're able to move freely without encountering another defect. Now this only occurs, so if you were to plot, for example, the yield strength versus grain size, it's going to increase until about this value of 10 nanometers, and then it will decrease sharply. Now, why is that? Well, at 10 nanometers, our dislocation has a size probably on the order of, nanometers. So you're only going to be able to fit about 1 or 2 dislocations in a grain size of about 10 nanometers on average. So you're not getting that dislocation pile up. So it's not more, it's basically, because there's only 1 or 2 dislocations in there, you're not getting that dislocation pile up and resistance to dislocation motion. Finally, you can have precipitate or particle strengthening. Now, the key thing you can kind of see here is I have 2 energy, when I have a precipitate and I have a dislocation line. So I have a precipitate or a particle that's nucleated in my system. This dislocation line is going to move and it's going to have to make a decision. I can either cut or I can bow around this particle. If I cut, the energy penalty I have to pay, the one thing I don't want to do is, I don't want to create surfaces. So if I cut, I'm creating 2 surfaces here. So that's my energy penalty. So that's the price I'm going to have to pay if I make the decision to cut. If I bow, I'm going to have to bow that line and create curvature. My curvature is 1 over the radius. And the radius here would be the radius of my particle. So I can see, when am I going to cut? And you can kind of see this kind of curve that shows your change in yield stress versus the radius of my particle. And it basically increases to maximum and decreases. Do I want to cut large particles? No. Why is that? Because if I cut large particles, I'm creating a lot of surface area, right? So I want to actually cut large particles. Or excuse me, I don't want to cut large particles. I want to bow around large particles. Why? Well, my curvature, if I have a very, very large particle, then my curvature is very, very low. So I'm not creating much curvature. Again, the Earth is huge. It has a large radius. It is not flat. I want to emphasize that. I don't want to get this video taken down. It has curvature, but it's very, very low. So large particles, there's a low penalty to bow around them. Now, small particles, this curvature penalty will increase significantly. And if I have small particles, well, I could cut those because I'm not creating much surface area, so I'm going to cut here. So that's the distinction. Now, a cool thing happens. What if I have a system like this, where I have only a few particles of different sizes versus lots of particles? So if I go from system 1 to system 2, how will this curve change for system 2? Well, I have a lot more particles, right, that are going to provide resistance to my dislocation line. So, and am I going to want to cut here? Probably not, right? Like I'm going to want to bow around a lot because if I cut through, there's going to be a lot of surface area created. So I'm going to probably want to shift to where I'm only going to cut very, very small particles, and my yield strength may increase and my maximum may shift to the left, right? And if I were to go from state 1 to state 3, where there's only like one particle, you may see, again, a lower shift, right? Because there's not as much resistance to my dislocation line. And I'm fine with creating a surface area for one particle. So you can kind of see those differences in those shifts. And hopefully you have fun in your p-set with those types of problems. There's some additional information about yielding mechanisms, and we'll see that a little bit in the lab. But next time we're going to talk about time, temperature-dependent plasticity, and specifically creep and deformation mechanism maps. So we'll see you then. Thanks. Bye.